All right, any questions before we get started? So no questions about anything? So hopefully you had a chance to get some free food before class and sign up for clubs. Let's see, so let's go back and talk about naming these compounds. And so now we're doing, how do we name covalent compounds? And so unlike the ionic compound, and we may need to do some review on this, but unlike the ionic compounds, the formula cannot be determined from its constituent elements. So you can't just say, for example, nitrogen oxide. So that wouldn't make sense because looking at all these examples here, well, it doesn't specify how many. So you can have a 1-to-1 ratio, 1-to-2, 2-to-1, 2-to-3, 2-to-4, 2-to-5. So just saying nitrogen oxide or anything like that wouldn't work. So it's not like the ionic compounds where, again, they have these set oxidation states. And so we're just going to be looking at these molecular compounds with just two different nonmetals. And so all you do is you have your name of your first element and then a prefix if necessary. And so this prefix is just used to indicate the number of atoms present, but just like you probably know from CO, if there's only one of the first atom, you don't say mono for that first atom. So you would just go carbon, and then now you would use your prefix of monoxide. And then you change the ending to "ide" again. And so we have all the prefixes there. So mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa 8, nona 9, and deca 10. And so again, only the mono prefix is omitted if there's just one atom of the first element. So now let's practice a couple of these. So take a few minutes, ask your neighbor, ask your friend, what would you call all of these compounds? So let's go over them. So what do we get for A? So Ni3, what would this be? So nitrogen, but then what do we need to do? So don't forget your tri, and I believe this one has 2 I's, so triiodide. So yeah, that's the correct spelling with the 2 I's. You know, that looks kind of funny. And you could just quickly sketch what that would look like. Just kind of practicing. So this is just kind of your typical group 5 compound, right? Bonded to 3 things. And we'll go over the geometry, but I'll say it right here. So trigonal, pyramidal. So just very classic geometry. All right, B. Phosphorus pentachloride. Exactly. And so this one not as typical, but was kind of our standard expanded octet geometry. And you don't need to know this geometry, but I'll still give it to you. So trigonal bipyramidal. I was just making sure it was not on your list. And then what about the last one?
Would it be phosphorus for decasulfide?
So instead of the 4, what should we put? Tetra. So tetraphosphorus. And decasulfide. So don't forget covalent compounds. Remember those nonmetals plus nonmetals. So all on the right side of the periodic table, you have to use your prefixes. And I'll just paste what this looks like. I did not want to draw it for you. But this is actually, it looks funny, but a lot of organic structure is going to take this shape. So adamantane would be like the carbon analog of this. There's also P4O10, which would be very analogous, just obviously swapping out the sulfurs for oxygens. And so it has these 2 6-membered rings kind of fused together. And then you can at least appreciate, so we have a phosphorus sulfur double bond. So we're seeing like, yes, that happens. And actually, let's name this one. So what if I had given you P4O10? Oops, sorry. So what would the name of this one be? Or tetraphosphorus, right? And then what about the last part? So deca, except for the spelling. this one, okay. So this one has deca oxide. What I should have asked, so this is actually the same compound, P2O5. So I don't know why, but sometimes people just refer to it by its empirical formula, even though it doesn't reflect its molecular structure. But this one, I wanted to point out this one because of the val. So you would have diphosphorus, and then you have pentaoxide. But if you have two vowels kind of next to each other, in some of the cases you drop that first vowel, so it just becomes pentoxide. But again, those will be the scenarios. I try not to be too picky on your spelling. You know, at least make it decipherable. Try your best. It's hard for me to give partial credits on those "ide" versus "ite" though endings. So you may see that on your quiz, because remember, "ide" is more of the atom, but then "ite" could refer to some sort of polyatomic. So in that case, it's hard for me to give you kind of grace and flexibility. So just watch the little spellings there. Again, I'm not trying to penalize anyone on these, but just try to watch the little things. And so now let's make sure we all know how to get a formula mass. It's pretty self-explanatory, but let's go over it. And so we have what's defined as either the molecular mass, but it's also can be defined as either the mass of one individual molecule, and that would be in AMU, or it's also 1 mole, and that would be given in grams. And so that's, again, the number straight off the periodic table. We kind of mentioned it before, that this could be 12 AMU, if we're talking about one individual carbon, or it can mean 12 grams per mole, if we're talking about big macroscopic units of chemistry. So if we wanted to find the molecular weight of water, we just have to add up the numbers, and you know, you're going to have a little bit of differences with whatever periodic table you're using and how much you choose to round. So I kind of leave that up to you. I usually say, you know, go to after the decimal point just to give yourself something to work with, but you know, often we round oxygen to 16, or hydrogen, some people just round to 1. So there's always going to be a little difference, but all we do is we pull the numbers off and then multiply it by how many we have. So we have 2 atoms of hydrogen, and so we just pull it off from the table. So you could use 1.008 if you wanted to be really precise. They rounded, then plus grab the mass of oxygen, so you could use 15.999, and often rounded to 16. And then, of course, they just added them up. I'm just being really explicit here. 1.01 or 1.008 times 2 plus 15.999. And so we get something really similar, so 18.015. So something like that for your answer. And again, either atomic mass units for one individual molecule. And we could also say, though, that 1 mole of water has a molecular mass of 18 grams. So let's do one. Practice. So aspirin has a formula of C9H8O4. So see if you can figure out what the molecular weight is.
2 decimal points. Is that okay?
Yeah, that's just my general broad rule, but you'll kind of, just get a feel for it. Did we get an answer yet? What'd you get?
180.16.
So 180.16. Is that what other people got? I might double check. I think 180 sounds good, and I saw some nods.
How many decimal points did you say again? Or that you wanted?
So I was just kind of roughly saying, like, you can report the numbers to kind of 2 after, and then you can go with that with the rounding. But, I expect a bunch of discrepancies, so it should have been 12 times 9 plus 1 times 8 plus 16 times 4, 4. So yeah, somewhere around that ballpark would be good. And so now let's cover what molecular geometries you have to know, and then some classic examples. And so trigonal planar. So some of the classic trigonal planar examples are going to be like boron trifluoride. And so this would be a covalent compound. And so this is what it looks like. And so boron, it's kind of one of those odd ones. We haven't talked about it too much. But boron, it only has, well, how many valence electrons does boron have? So I see a 3, so 3 valence electrons. And because it only has 3 valence electrons, when it makes these covalent compounds, it tends to only make 3 bonds then. But these boron compounds are also highly reactive, because what's the problem here? What's not being satisfied? Octet. So it only has 6 total electrons. And so that means, though, that these boron species are really reactive, so they will react, with water, of course, in the atmosphere, and you can make boron-oxygen bonds. There's a lot of, I think it's triethyl boron. And so this is an organic molecule, but ethyl just refers to two carbons, but this like totally ignites in air in like a green fireball. So that's one example of trigonal planar. But then you can also have, so carbon also makes trigonal planar structures if it has one double bond and then two single bonds. So this is kind of the general form. So one example would be acetone. Let me draw that better. So this is trigonal planar. So it's carbon attached to three things. And so when you're looking at the geometry, you're also just focused on like how many atoms it's connected to, not the number of bonds. So it still has 4 bonds always, but we're saying, okay, it's carbon with 3 things, so that gives us our trigonal planar geometry. And you might also hear the term, so for carbon, this would be sp2 hybridized. And the way you can remember it, well, there's 3 things attached to it. And so we need 3 orbitals coming together. So that's 1 s and 2 of the p's to give you that looking structure. So that's an sp2 hybridized orbital. And again, that's just referring to like where the electrons are going, is they're basically saying, okay, we're going to occupy these positions so we can participate in this sort of bonding. So tetrahedral, so somebody give me one of our classic examples of tetrahedral. It's also the simplest hydrocarbon. So there's a carbon somewhere. And so how do we get tetrahedral? 4 things attached to it. Hint, what's the other greenhouse gas that's not CO2 that now they're making a big deal of? I don't think O2 is a greenhouse. So it's just methane. Remember, now they're talking about like the cow farts. The cow farts are going to kill us all, apparently. I don't believe it. But all we care about, so this is methane. And so this is just always shown as your classic tetrahedral example. So we have carbon bonded to 4 things. And we can also, so for this carbon, this would be sp3 hybridized, if you see this term pop up. And all that's saying is that carbon has an s orbital, 3 p's. They all came together to make this sort of lobe-looking structure where the electrons, again, are located, and that allows it to make 4 bonds. And so we saw that with all the other group 4s, like silicon tetrachloride, germanium, bromide, tetrabromide. So you could go.
So this molecular geometry, is that like what they're showing on the P table when you're looking at like the different orbitals?
No. Well, it's kind of like yes and no. So if we look at carbon and the electrons, so what it shows you, because the only thing that it's showing you with this picture is like the valence orbital. So that's just showing you like one of the p orbitals, but it's not like reflecting how carbon tends to hybridize to different things. So you would take like the mathematical addition of all those. So mathematically, you take, you know, px, py, pz plus an s orbital, and that equals to that picture. And so we just kind of do it pictorially, and if obviously someone has done it mathematically at some point, that's what computational chemistry is for, and we just kind of appreciate the pretty pictures. And so other times you would have tetrahedral. Let me pull up a picture. So this is cyclohexane. So all this is a six-membered ring of carbon, but I'm just pointing out, so each carbon, right, the center of it, it's still tetrahedral because it's carbon bonded to four things, so 2 hydrogens and 2 carbons each. And so that gives us tetrahedral at each one of those carbons. All right, trigonal pyramidal. So what's our classic trigonal pyramidal example? If you did lab this morning, you made that gas that I'm looking for. What was the only thing you could have sniffed in today's lab? Ammonia. So NH3, so that's our typical trigonal pyramidal compound. And of course this should have matched with our nitrogen triiodide picture, so same thing. And so you can also see how it's a derivative of the tetrahedral geometry. So it's related to ammonium. So let's just review. So ammonium is nitrogen with 4 hydrogens attached to it, overall plus charge. So there's ammonium. So ammonium has a tetrahedral geometry. So tetrahedral, and then you can just kind of think about it. And what happens chemically is a base will come along, pluck off the hydrogen from ammonium, which is why sometimes ammonia is given as this formula, ammonium hydroxide. And you're like, wait, that doesn't make sense. But what you'll learn is this hydroxide comes along, plucks off this hydrogen, and makes ammonia. So now we have ammonia. So again, same base structure as our tetrahedral, just now we have a lone pair instead of a substituent, so giving us that trigonal pyramidal geometry. And so this would also be sp3 hybridized, since we have 3 bonding groups, so 3 bonding plus 1 lone pair. And you can go crazy with the other derivatives as well. So of course we mentioned phosphine before. Could do PCl3 just to change it up, or phosphorus trichloride. And then the last geometry that you guys need to know is bent. And so can anyone think of the classic example for bent?
Would it be H2O?
H2O. So good old water, our little Mickey Mouse molecule. And so bent is also a derivative of tetrahedral. So now we've taken off 2 bonding pairs, and we have now instead 2 lone pairs, and then of course still 2 bonding pairs left. So 2 bonding pairs, 2 lone pairs. And then there's actually another type of bent. So I'll give y'all a minute. So see if you can come up with the structure of this compound, SO2. We'll go over why it's significant. Apparently there's a lot of free food still in the Fiesta Latina, so if anyone wants to run out and get food, like, just totally do so. You get food? Yeah, go for it. They had like beef tacos, chicken tacos. All right, let's take a 10-minute break. People need to get their food. Any questions in the meantime? Gotta take advantage of free food opportunities. Sign up for clubs. Yeah, do it. Get food. Take a 10-minute. You guys have it a little rough on Wednesdays, like lab, class, lab. Oh, you don't have the boot anymore.
I'm trying it. We'll see how it goes.
Any other questions from lab or?
I don't think so. I think we got to everything else. Weird. Okay. I guess we'll sneak into it.
There's the rest of your class